Hi, in the last video, we learned what is RAG and why LLMs need external knowledge. In this video, we will understand RAG system architecture and RAG system flow. So, end-to-end RAG system flow, let's understand it. An end-to-end RAG system is a sequence of components that together produce accurate, context-aware LLM answers. We start with source documents, PDF, Word files, web pages, APIs, and even databases. Those source goes through chunking. We split content into retrieval friendly sections to improve relevance. Next, we create embeddings, dense vectors that capture semantic meanings and store them in a vector database. At query time, the user question is also embedded and we run similarly search against the vector store. We retrieve the top k best chunks, commonly 3 to 5 depending upon complexity. Then we build an augmented prompt, order the chunks, dedupe overlaps and stay within tokens limits. So the LLM generates the final answer grounded in that retrieved context, which reduces hallucination. Overall quality depends on tuning every stage, chunking, embedding quality, retrieval settings, and prompt assembly to maximize relevance, accuracy, and reliability. So let's understand the importance of clean and structured data. The ingestion layer is the backbones of RAG systems. If ingestion is weak, retrieval and generation quality will suffer because RAG grounds LLM answer in external knowledge. The accuracy, formatting, and completeness of what we ingest is critical. Source can be PDFs, Word docs, databases, web pages, and third party APIs. And each brings extraction challenges like image, messy structure, inconsistent headings, or mixed language. A strong pipeline pre-processes context, text extraction, normalization, cleanup, metadata enrichment, and noise removal. So, raw data becomes standardized text ready for chunking and embeddings. Knowledge engineering matters here. We decide how to, domain info should be represented, labeled, and segmented so retrieval stays semantically meaningful. Poor ingestion propagates error downstream, irrelevant chunks retrieved, weaker semantic matches, and misleading LLM output. Robust ingestion does the opposite. Best embedding, fast, more accurate search, and high quality context for prompts. So, at scale, we need discipline around data mapping, validation, version control, and document lifecycle management to keep the knowledge base clean and continuously improving. Now, let's understand choosing effective chunk size and structure. Chunking strategy. Chunking directly drives retrieval quality, context coherence, and ultimately answer accuracy. We chunk because LLMs have tokens limits. Sending whole documents into the context window is not feasible or efficient. Good chunks are self-contained but still preserve semantic continuity with surrounding content. Key trade-offs is granularity. Small chunks improve precision but can lose context. Large chunks remain meaning but may add noise or weaken semantic matching. Domain matters for technical content. Semantic chunking often work better for narrative structured text. Fixed size may be enough. Ranking choice after embedding quality, retrieval relevance, and how coherently the LLM can synthesize the final response. Best practice is to test with real queries and metrics like recall and relevance. Then tune chunk size and overlap to find sweet spot. So, role of embedding in semantic search. Let's understand it. Embedding are semantic backbone of RAG. They represent both documents and queries as dense vectors that capture meaning and relationship between concepts. Unlike search, embedding enable semantic retrieval. So we can match synonyms, paraphrases, and conceptually related terms, which is critical in enterprise where technologies varies across teams and documents. High quality embedding help the vector store retrieve conceptually meaningful chunks, not just textually similar ones. Modern embedding models like sentence transformer or domain specific embeddings improve accuracy by encoding deeper context. So finally, organizations should periodically re-embedded content to benefit from newer model and keep alignment with evolving domain knowledge. So, managing and searching vector representations, designing efficient top K retrieval. Let's understand it. The vector database stores high dimensional embedding vectors and enables fast similarly search over them. A query time, we compare the query embedding to store vector using metrics like cosine, distance to find the closest matches. Vector store also support metadata filters, hybrid search, and index optimization, critical for precision and governance. Good retrieval depends on tuning index type, cluster partitioning settings, and search accuracy parameter to balance relevance versus latency. A well-configured vector store returns the most contextual relevance chunks quickly. If indexing is poorly managed or metadata filtering is missing, retrieval quality drops and you get irrelevance or misleading context. So, as repository grows, the vector database becomes central to keeping RAG fast, accurate, and reliable at scale. So, the retrieval layer connects embedding to generation by selecting the best document chunks to send the LLM. Top K is a key tuning knob. Too few chunks can miss critical context. Too many can blow tokens, limits, or introduce conflicting information. In most enterprise cases, top K of 3-4 work well, but higher complexity domains may need adjustment. We also choose retrieval methods, pure vector search, keyword filtering, or hybrid retrieval that combines lexical plus semantic matching. Hybrid retrieval is often more robust in domains with strict technology or compliance needs. To improve quality, retrieval should include relevance scoring, deduplication, and optionally re-ranking. For example, with cross-encoder models. So, when retrieval is engineered well, LLMs get accurate, non redundant, context rich evidence, directing improving response reliability. Building high quality prompts with retrieved chunks. Let's understand it. So the context construction layer turns retrieved chunk into a clean, usable prompt for LLM. The goal is maximize relevance and signal while minimizing redundancy and wasted tokens. Core steps include ordering chunks logically, removing duplicates, and adding domain specific instructions that guide how the model should answer. For traceability, especially in the regulated environment, we may add headings, metadata, timestamp, and source identifiers so output can be audited. Token management is critical. Too much context can exceed limits or dilute focus. Too little can omit key facts. So, we balance context size to keep the model focused while still providing enough evidence for accuracy. LLM generation layer. Let's understand it. The generation layer is where LLM reads the constructed context and produces the final answer grounded in retrieved evidence. RAG reduces hallucination, but it does not eliminate them. So, prompt design, clear system instructions, and high relevance context still matters. The model is very sensitive to how the context is phrased and structured. Clarity and formatting directly impact output quality. Simple guardrails instruction help a lot, like answer only using the provided context, and if the answer is not in context, say it is not available. So generation also involve creativity versus precision trade-offs. For enterprise scenarios, compliance, legal, technical guidance, precisions, and faithfulness to context should be prioritized over creativity. So, evaluation and feedback. Let's understand the measuring RAG quality and reliability. Evaluation is critical to keep RAG system accurate, relevance, and properly grounded over time. We evaluate across key dimensions: retrieval relevance, answer faithfulness to retrieved chunk, completeness of coverage, plus latency and cost. This is not one time activity. Evaluation must be continuous, not just during initial go live. A strong feedback loop help pinpoint where issue organize. Chunking, embedding, retrieval setting, or prompt context designs. Performance can drift as docs changes. So periodic audit, re-embedding, and index refreshes are essential. So diagnosis and preventing system weakness. Let's understand it. Even strong RAG system have common failures mode we must plan for. Chunking is a frequent issue. Chunks that are too large overwhelm the context window, while chunks that are too small lose meaning and underserve the model. Embedding can also fail if they do not capture domain nuance. Retrieval quality drops even if the pipeline is correct. Vector store can return irrelevant result when metadata filtering is weak or missing. So, RAG is not a feature, it is a architectural pattern. It separates knowledge storage from reasoning capability. In the next video, we will build this architecture step by step, not using shortcut, not using magic framework, but building the system from first principle. So, see you in the next video. Thank you.